All right, so without further ado, take it away, John.
Hi, I want to thank everyone for showing up. I really appreciate this. And I really want to thank the committee here for letting me do a presentation. That really does mean a lot to me. What I have to present is found in the books, the manuals, and I can guarantee if you read them, you're probably not going to be totally lost. So it kind of helps if you have someone that knows, has figured out what's going on, has a different perspective than what the instruction manuals present. It might kind of clarify some things, and if you could see things from maybe my perspective rather than the instruction manuals, you know, all those reference manuals perspective, which everyone reads and no one can make out. No one understands those. So I'll go ahead and present what's going on. Okay. Oh no.
There you go. Okay.
Oh, too many characters. That's not going to work. Okay. That's what I got to type in the invisible background. Now, when I hit my return key, you will not see anything because, and the reason is because the basic system loads it in main memory, and in order to display it, you have to put it in both auxiliary and main memory both. So it will not make sense. So now I go ahead and run the other routine that'll actually put it on the double high-res graphic screen. Okay, now here's how we're doing this. 4 sets of pixels in a row will make white. Okay, got that? And if you clear 4 pixels in a row, you'll get black. Now the resolution of these is a resolution of 560. By the way, I don't know. I want to take just a little bit of brief time. I don't know how many people are aware that the standard high-res graphics technically has a resolution of 560. It's stated to be 280, and I understand where they're coming from. Let's be clear on this. Colors 0 through 3 on high-res have a resolution of 280. But keep in mind that colors 4 through 7 also have a resolution of 280. And I want to point out something. Because they're the same numbers, you might say, well, that's not saying anything different. It happens to be, and I don't know how many are aware of this, that 280 on the second group of colors, 4 through 7, plots in between the pixels of colors 0 through 3. And since black and white are on both palette sets, this actually means that the colors of black and white technically have a resolution of 560. Okay. Now on double high res, we're only at 1 palette set basically because we're supposed to keep the most significant bit cleared all the way through. And we can plot those same pixel groups anywhere on the screen. But it's got to set 4 in a row to display white, and you got to clear 4 in a row to display black. Now, I don't know if you noticed this, but the pixel pattern and byte patterns do not match. But they do on the color black. Because if you have 4 consecutive zeros in a row, okay, we'll plot black, right? And now that 0 would show up in the byte as a 0, but it also displays in the pixel pattern as a 0 as well. Now this doesn't happen with the color white. In order to display white, you set 4 consecutive pixels, which is technically an F. But let's say you set another group of 4, it'd be an F also. But you can't do that on 1 byte because the most significant bit's not used, so the pattern would be a 7F, 7F, 7F. Although the pixel pattern still is an F, 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 F all the way across the screen. Okay? On black, it's going to be all zeros across the screen. Let's go on to something a little bit more different than just black and white, because no one's really interested in those two. Okay? If we set every other pixel all the way across the screen, Now we got two ways to do it. We could either start at the leftmost being 1 0 1 0 1 0 1 0 1 0 1 0, or you can start out with a 0 and followed by 0 1 0 1 0 1 0 1. Now, here's how to look at this. A 0 1 0 1 is a binary 5. Technically speaking, we got a 5 5 5 5 5 as far as pixel pattern, but that's not the byte pattern. And if we change all ones to zeros and all zeros to 1, we'll have a 1 0 1 0, which is a hexadecimal A. A. And I believe that this is the very reason why on low-res graphics, colors 5 and colors 10 are the two gray colors. Okay? But which gray goes to which? I mean, the 2GS defined 5 as a dark gray, and 10 is a light gray. Which pattern starts which one? This is really interesting. We're going to start with this A value. The least significant bit of this is the far right pixel, which the very far right pixel plots to the very far left of the screen. So when you move right to left in the byte, you move left to right on the screen. Oh boy. Now who came up with this madness? Not only that, oh, you're going to love this. The byte on the right side displays the 4 pixels on the left. The ones on the left side display the 3 remaining pixels on the right side. Oh no. So it's not real easy to follow through, but take note. This always follows through. Here's something that's easy to follow. If you can't remember anything, try to remember this. The least significant bit, which is the far right one, of the first byte is the very leftmost pixel. And with being a 0, it's a 1 0 1 0 for an A. Well, that would mean, let's see. Where's the patterns I put up here? Can't even tell it. Oh, here's one of them. Where's the other one? I put both grays up here. I could have swore it. Well, anyway.
At the bottom by the right.
Oh, no.
Line above it.
There it is. I couldn't find it. I knew I wrote it in there. But the reason why this is the least, this is the leftmost pixel of the screen. It's cleared. Got it? But the reason it's cleared is because the least significant bit of an A pattern is also cleared. As we move, let's just do it within the pixels, okay? The 8th column doesn't show. 1, 2, 4, okay. This is the 8th column of the A. 8, 4, 2, and 1. The 8 doesn't show up because it would set the most significant bit, but it would be a 1. It's picked up on there. But anyway, it would go, the 8's a 0. That's why this comes as a 2. So you got a 0 in the 8th column, a 0 in the 4, the 2 set, and the 1 is a 0. So this makes these 3 plus the 1 to the right of that on the byte pattern, which is also a 0, is a 2. While these 4, the 8's columns, the 4's column, the 2's column, 1 column, it's hard to read these backwards. You don't think that way. You would think on hexadecimal that this would be a 5, because that's how it reads in most people's minds. It's not. It's an A. It's because the 8's not on the left. It's on the right of the 4. Okay? Now, notice if we flip all 1s to 0s and all 0s to 1. Oh, wait, there's something else. Oh, God, I forgot to mention one of the most important things. Not only is the least significant bit the farthest left, that's for a 1. Here's the other I want you to remember. Oh, this is really important. The second byte in the pattern, all colors match low-resolution graphics. In other words, this is color equals 5 in low res. It's done by putting 2A 55, 2A 55. Now because bytes 1 and 3 are the same, and notice 2 and 4 are the same, this has twice the resolution of, say, this one here with 33, 66, 4C, 19. That's because all 4 numbers are different, so it can't be the same resolution. It's actually half. That's technical, okay? By the way, it's true on high res, the colors of green, purple, blue, and orange technically have a resolution of 140. That's true on high res, but it's also true on double high res. Okay? Now, I want to show you this one. Notice all ones are flipped to zeros and all zeros are flipped to 1. This is 1, 2, 3, 4, 5, 6, 7. It'd be a 0 there in the 8s. So it's a 0, 1, 0, 1, which is a 5, 0, 1, 0, 1. So it starts, the pattern starts out 55, then it's 2A, 55, 2A. This is the pattern for light gray. Notice it goes all the way across the screen. If our pattern starts out 0, 1, 0, 1, 0, 1, 0, 1, 0, we will draw a dark gray line across that screen on the 5th color. If we start out with 1, 0, 1, 0, 1, 0, 1, all the way across the scan line, it'll print a light gray, and the resolution is 280. They're the only 2 colors that have that resolution. Just like the black and the whites are the only 2 colors that have 560 resolution. The remaining 12 colors have a resolution of 140. Okay? Yeah, the remaining 12 have a resolution of 140 pixels, technically. I mean, that's the workable resolution. And now, I want to show you something here. The 4 colors that would display on high-resolution graphics, they have the colors of 33, 66, 4C, and 19. It'll start off with a different one for whichever different color. But which one goes to which color? And this is, notice, a 33. It would start off 1100, 1100, then a 1100, 110. All 4 colors that would display on high res follow set 2, clear 2, set 2, clear 2, all the way across the scan line. Okay, but which one is this? Well, remember I said that the second number aligns with low resolution graphics. The second number in this pattern is a 66. Therefore, in low res graphics, if you type color equals 6, you would set a medium blue. And true, yeah. This 33, 66, 4C, 19 is the pattern for medium blue. Now, here's something that's really fascinating. This happens on high-res graphics, too, not just double high-res. Flip all ones to zeros, all zeros to 1. So instead of going 1, 1, 0, 0, 1, 1, 0, we're going to start 0, 0, 1, 1, 0, 0, 1, 1. This one right here. We flipped all ones to zeros, all zeros. Now, to figure out what the value of this is, well, 1, 2, 3, 4, 5, 6, 7. This is on the next byte. So it's a 0 in the 8s column, a 4, 0, 0. So the value would be a 4, and the rest, a 1, 1 in the 8s and 4s columns is a C. Well, notice the next 2 are cleared. So that pattern's definitely a 4C. No question whatsoever. The pattern that starts out 4C, 19, 33, 66. Which of the 4 high-res colors is it? And remember, the same rule applies. Color equals 9, which is orange. Now that's true on high-res graphics. When you flip all ones to zeros and all zeros to ones, you would flip a blue to an orange or an orange to a blue. This is true on double high-res as well. Oh, hey, before I go on, notice my pretty colors. I like that because I've arranged them in the color they would show up in low res. This would be color equals 1, color equals 2, this is dark blue, red, dark blue, purple. Dark green, well, the grays will look the same because this is a 2E, but this is supposedly a dark gray. Medium blue, light blue, brown, orange.
Purple.
Yeah, wait a minute, purple, let's see. Yes, you're right, that should be 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's not, it's pink. The one after this was purple. No, wait a minute, it can't be purple. Look at, they don't look the same. They do on a, this is because the resolution's really not a high resolution. It's not real clear. But yeah, the actual color would be pink. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. Color equals 11 is pink. Yes, Joseph. I'll listen to you.
Oh, I was figuring out the color mixing. It makes sense. Okay.
Okay, yeah. Now try to remember this pattern because this is where I'm going to take off from. 0, 1, 1, 0, 0, 1, 1. So it starts off with a 0 and then I got 2 set. Now it'll be all messed up because it's in loaded in main memory. Now to straighten it up. Okay. Again, the pattern I was talking about is 0, 1, 1, 0, 0, 1, 1. Let's see. 1, 2, 3, 4, 5, 6, 7. There's only 7. 4, 6, 7. So that'd be a 0. Oh, it starts out with a 6. Everyone recognizes that a 0, 1, 1, 0 is a 6. Then same thing here. 0, 1, 1, 0 is a 6. So the pattern starts off at 66. It's 66, 4C, 19, 33. Okay? The important one here, color equals 12. The C is a decimal 12, and in low-res graphics, color equals 12 is light green, the same green that displays on high-res. Okay? Now let's say we used to flip all 1s to 0s and all 0s to 1s, so the pattern starts out 1, 0, 0, 1, 1, 0, 0. Got it? Now our pattern becomes 19, 33, 66, 4C. And in low-res graphics, color equals 3. That's gone. Remember, it's on the bottom of the first page that I got rid of. But color equals 3 is purple. Now notice the relation of light green and purple. All 1s flip to 0s, all 0s flip to 1s. These 4 colors, which is colors, equals 3, 6, 9, and 12. Notice it's every third one. I don't know how many people have noticed that on low-res graphics, every third color is one of them that displays on high-res graphics. Now, from a technical point of view, that's because every third one sets 2 pixels and clears 2. For instance, a 3 is a 0, 0, 1, 1, then a 0, 0, 1, 1. While a 6, it is a 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Okay? 9 does the same thing, but the pattern starts at 1, 0, 0, 1, 1, 0, 0. And C is the only, which is 12. It's the only other one that'll do that. None of the other colors follow that pattern. Only those 4 in particular. And that is, I believe, the real reason why those 4 colors show up on high-res graphics. I think what happens is technically, you may be plotting 1, like you plot H plot 5, 5, but it'll plot 2 in a row on the 560 resolution. You can't plot just 1 pixel. It'll plot the one right adjacent to it in all cases. Let's cover something a little bit more interesting than that, because we're not just interested in those 4 colors, the 2 grays and the black and white. How about something really nifty? I'm going out 27 bytes, because on the 28th, it repeats again. So the byte after this one is the same as that. Notice we got 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, all the way across the scan line is that. What have we got here, though? 1, 2, 3, 4, 5, 6, 7. Here's the split of the byte. It's a 0, 0, 0, 1, 0, 0, 0, 1. That's a hexadecimal 11. Okay, so it's 11, 22, 44, 0, 8 is the last one. And so this is effectively the same as typing in color equals 2, which is dark blue. Okay, so dark blue's pattern starts out as 1, the very far left pixel's cleared, and then you got 3 set. The very far left pixel set, and then you got 3 consecutive cleared pixels. It's 1, 0, 0, 0, 1, 0, 0, 0. Let's, if we shift a 0 into here and move all these down 1, now we change our pattern to 22, 44, 8, and the last one's an 11. In this case, the color pattern now is a color equals 4. And in low res, color equals 4 is dark green. Okay, let's go on to the next one. say we shift in yet another one. 1, 2, 3, 4, 5, 6, 7. 0, 4. Wait, 0. The 4's column set. And in this one, this is 8, 4, 2, 1. So it's a 44. 44, 8, 11, 22. Okay. In this case, its color equals 8, which is brown. Okay. And the last one that follows this pattern here, we start off with 3 consecutive clear bits. It goes 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, okay? But since it starts off with 3 consecutive, notice 1, 2, 3, 4, 5, 6, 7. The 8's 0, the 4's 0, 2's 0, 1's 0. That means this one's a 0. Then this is in the 8's column, and all the rest is 0. So it's a 0, 8, 11, 22, 44. Color equals 1 in low res is red, okay? And so thus, this is the pattern for red, the brown, dark green, dark blue. Okay, that's what this says here. I just kind of pointed it out. I've got all these memorized anyway. I went over so many times. That's not all. There's still quite a few. Let's see, how many I displayed. Let's see, I got the black ones. Wait a minute. The black, the white, the 2 grays, the 4 that display on high res, and then there's 4 that follow this pattern. Well, that's a total of 12 colors. There's a remaining 4 colors, okay? And I'm going to go out how they work. Here's the last page. Now notice if we flip all 1s to 0s on dark blue, all 1s to 0s and all 0s to 1, well, look what we got now. A 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0. Let's see, 1, 2, 3, 4, 5, 6, 7. The 8's would be a 0, so it's a 0, 1, 1, 0, which is a 6. A 1, 1, 1, and the least significant bit 0 is an E. So this value is a 6E. This makes this a 5D. This is the end of the second byte, which is a 0. 0, 1, 1, 0 is a 5. Right? A 1, 1, well, let's see. Oh boy, I'm getting lost in this mess. I better not trust my instincts to this. But it's a 5D, okay? There's a 6E, 2, 4, 6, 7. Wait a minute. 1, 2, 3, 4, 5, 6, 7. You get lost in this mess. 0, 1, 0, 1. Oh, the pattern is 1, 1, 0, 1, which is a D. It is a 5D. This one, notice, 5, 5. Ooh, I don't want to follow that through. Now, it's a nightmare following that through. But anyway, it's 3B. I wrote them down here, 77. Oh, yeah. 5D, 3B, 77, 6E is the pattern. Okay, and notice in the first one we had, this one right here, where it's the 5D is the second byte, a hexadecimal D is equal to a color number decimal 13. So in low res, color equals 13 is yellow. Okay, so in other words, this pattern is the pattern for yellow, which is 6E, 5D, 3B, 77, all the way across the scan line. With this one, we got 5D, 3B, 77, 6E. Oh, the B is the important one. Color equals 11, which is pink. Notice that pink is the opposite of dark green. In other words, you flip all 1s to 0s and all 0s to 1. You'd flip dark green to pink or pink to dark green. Same thing with blue and yellow. You flip all 1s to 0s on 1, 0s on 1, flip them the other way, and you'd flip a dark blue to yellow or a yellow to dark blue. On this one, notice we start off 1, 1, 0, then 1, 1, 1, 0, 1, 1, 1, 0, 1, 1. On all of these colors here, it's 3 consecutive set pixels and 1 cleared one. Okay? So we go, Right here, 110, 1110, 1110. We end up having a 3B to start off with, 3B, 77, 60, 5D, and then low-res color equals 7 is light blue. So this is the pattern for light blue. The last one that does this is the one that's opposite of red. It starts off with 3 consecutive pixels. 1110, 1110, okay? This one would be aquamarine. And now this is how the 16 colors are done. How many minutes did I use?
We got about 20 minutes left.
Whew. Oh, good. I'm glad about that because I thought just explaining this would take 45 minutes. I'm glad it didn't. Once again, I kind of arranged this in the way, let's see, I think this is 5, 6, 7, 8. Boy, that brown looks horrible. Well, I've got it right. No, these are the top, that's white. Oh, that's 14, 13, 12, 11, 10. Oh, okay, there's where this is supposed to be a light gray, and it doesn't look much like a light gray. Not hardly. I don't know. To me, it looks the same. But remember, it's a 2E, though. This is supposed to be pink. It looks purple to me. This is the light green, yellow. Yuck, what a horrible yellow. I'm hoping that when they come up with VGA cards that they could straighten these colors out and make them display better. And then the pattern goes, this is 14 aquamarine, white, black, red, dark blue, etc., etc. You know. That one's actually the third color, which is purple, dark green, dark gray. But I didn't just memorize these colors, I put them to use. Except for I don't remember what I call it for KansasFest 2016.
For anybody who, the opposite colors, if you have an iOS device or a Mac and you invert colors, you'll see it does the exact same thing with, if you match those colors with RGB values, it actually would flip the RGB, so, red, aquamarine.
Are they really the opposites on those?
And blue and yellow, yes.
They really are.
Yes.
But you see that, well, this is definitely older technology, but it seems like this may have, what Joseph Carter's referring to seems to be copied from this older technology that worked way back then. Oh, Becky, I'm willing to listen. I don't really know. I'm taking.
The colors are all generated because of the fact it's based all on the NTSC signal.
Okay.
The black and white, you see, the trouble is that in modern computers, the colors are either RGB values directly driving the 3 guns, or it's an index directly going into a color table. Very simple lookup. The Apple II's hardware is not built on that. It is built on the NTSC signal.
Okay.
So what goes on is that you have, each byte has 7 bits. The 8th bit is an actual half clock. That's what the other bit's for. What goes on is that the lowest bit is transmitted first, so on and so on, which is why you have the bits reversed as they are displayed.
Just like I said, yes.
They go out the NTSC monochrome channel, which is why on a monochrome display, the images are perfect. If that highest bit is turned on, what it will do is before it starts shifting out the data onto the display bus, it will wait 1 clock, 1 half clock, which is how, if you set that bit, it will shift it over 1 half, is how you can get the perceived resolution of 560 pixels across instead of 280.
Yeah.
So by using that under certain circumstances, you can actually shift some pixels on a byte boundary a little bit over, so you get some effects, especially some kerning and some things. They did this in Dragon Force.
Okay.
Now, how is the color generated? The color is a completely separate circuit. It's a completely separate signal because it goes through the NTSC color burst signal. This is how we got from black and white TVs to color TVs. What this does is that there's a 3.5 megahertz color carrier signal. what goes on is that on the Apple IIe, you have 2 bits, and all that is determined is to be a delay to start the color burst signal. It is synchronized to work with 2 bits on this Apple II or the Apple II screen.
Mm-hmm.
So what will happen then is that you will have one signal generating a monochrome image. Another signal, completely separate, is telling when to start the color burst signal.
Okay.
Color burst works by the color wheel. If you start at the beginning, it starts, I believe, with red. But if you delay all the way to the end of the slot, it goes to the other end of the rainbow. So basically, where it is on the rainbow when you hit the color clock or the color chroma signal is what determines what color displays. Which is why you have on old style TVs, there's a contrast and there's a chroma. All that chroma dial does is it compensates for the color clock and it says where to move it back and forth, which is why the colors get moved around.
Thank you, Becky. I didn't even know a lot of this stuff, but actually everything she said seems to match up to everything I presented. Everything matches, but I couldn't present the reason why because I didn't know.
Yep. And double high res, the way double high res works is, if you remember, you have one screen on one bank of memory, the other screen's on another bank. There's a reason for this. The Apple II runs on an 8-bit bus, meaning, and at 1 megahertz, you can only send data so fast.
Mm-hmm.
The engineers decided if you have 2 completely separate sets of memory, but access them at the same time, you've got truly a 16-bit bus. But it has to be on 2 physical separate banks of memory, which is why you may notice double high res, the memory's interleaved like this.
Yes.
Because what you're doing is you're using an 8-bit computer to write the 16-bit memory. So therefore, they could still run the main bus at the same 1 megahertz, but because it's reading 16 bits at a time, it goes double speed.
Wow, I couldn't even said anything like that. Thank you very much for your input, Becky.
Okay.
I really appreciate that. Let's see. I'm there. Huh. I'll tell you, I really did write something. How about that? Let's reboot it and try it on this disk. There. That's much better. I rebooted it instead. I don't know why it didn't work. I should have been able to just launch that right from the prompt. For some unknown.
You may have your soft switches in a specific way that your program can recognize.
Oh, yeah, that's another good thing. I want to tell you something. When I write, and it exits out through the quick code, it's a JSR to BF100, and then you got a 65 for quit, and then you got the parameter list. And before I even do that, I always try to flip the C05F switch so it switches back to standard high res. And then we keep the double resolution off. And I also try to make sure to send out the signal to shut the 80 column card off. I figure that's kind of considerate, because most people probably don't use it in those 2 modes anyway. Oh yeah. Hey, how about that? I wrote a short program here. It's more of a demonstration program. Pretty. I like the way they turned out. Yeah, a nice building, and the browns looks right. This is a light gray, dark blue. This is a light blue, yellow sun, light green grass. No, is it light green, or did I use the high res green? I can't remember for sure which one. But yeah. So I know how to
see the black and white signal on that. See how there's vertical bars?
Yeah.
Those vertical bars are the bit patterns of the black and white image you're seeing that's bleeding through the color burst signaling.
Let me.
That's why you have that artifacting.
What was that? You can't see it at this level unless you had a real magnifying glass. But remember, light blue was produced by having 3 consecutive set pixels and 1 cleared. So notice, and this is the same as that, other than you got 3 consecutive. This is brown, and you'd have 3 consecutive clear pixel and 1 set pixel. And but then you can't, and the resolution's not good enough. You can tell if the lines match up. But if it was a high enough quality, you could tell that the lines would match up on certain, certain patterns. If we go into the shack here, I'm going to hit the G. Oh, I was wanting to point out something. Notice that this is really crisp. It's not, but if I was to not get it lined up right, it wouldn't show up clearly, okay? So I got a shape table of all of the letters, and I have to shift them to a certain location depending on the color. Now on light blue and what's its opposite? Brown. Yeah, brown. Yeah. The offsets can be the same on both these colors. But by golly, if you try to put this on a yellow background, it's not going to show up very well. It'll show up, you'd still see the characters, but you'll see the color flinges, It's really bad. And inside is me and Rochelle. We're running the supply emporium. And then when I press the space bar, I got a different pattern. See, we got this is dark green and pink. And it's really neat. If you have a high enough resolution, remember that dark green and pink are opposites, and you'll see where the lines match up against the spaces. But you can't make it out on this quality here because, and it's really, I think, probably the fault more of the Apple II than it is the thing.
Well, never twice the same color for a reason.
Yeah, it's awful. And I'm hoping that the future solutions work better than the previous past. Now these are two other different colors. We got red and which one was it? It could be the aquamarine. If it is, then these would match up perfectly too. I don't want to play too much of this game anyway because I don't want to play games. But I had my heart set to it, but it takes so long going through these. And it's just temporary. I just wanted to show you how some of those matched up, I could pull up some of them, like out of the game's text files and show you several other colors. But the ones I really selected it on, I've done it on the pink, the dark blue. Oh, here, let's go into the boat. Because I didn't see dark blue, did I? I don't think I did. So let's go to the boat. Yeah, I got a female captain here. I think a few people might appreciate that. She advises you not to set sail, but that's not the important thing, not the game. I want to point out, see, the colors are real crisp against this. Because the characters are lined up correctly. Like I said, if I did not line them up correctly, this would not look good. It looks bad. It looks bad on a RGB monitor. It'll look bad on this too. It's kind of handy to know where they're at. Now, if I had the ability to display like how the 2GS, you remember in the 2GS, if you set it on monochrome, you can see the bit patterns a little bit better. And if you did that, you would see that, where do you see a solid white line going up there? You would see that falls exactly right in between those, three cleared pixels. In other words, to get the dark blue, it's a 1, the 1 would go at 4 there, then a 0, 0, 0. Well, I draw the solid white line there against those 3 zeros, because that gives you a nice white area to draw against. And actually, that's the reason why I chose the colors that I chose, as opposed to choosing gray, which, or the colors that display on high res. You got a nice white area to draw the character over, and you got it over 8 colors, and it really. Hey, does anyone have any questions pertaining to any of this? Does everyone keep up with what I have to say? Everyone understand? Does anyone have a different perspective than they did before? I mean, like you read the instruction manuals and not know what's going on, the reference manuals, and I mean, how many people did realize that that the second byte of the pattern actually does line up in low res? Not.
I didn't know that.
Yeah. And the thing about it is that it does it on all 16 colors, and I think that's an important, worthwhile thing to point out. And it still doesn't help you as far as getting something drawn on there, but at least I've revealed some important details, I think. Okay, I'm going to go ahead and cut this short so we can get started with the pizza then.
Yeah.
Oh, thank everyone for your time, okay? How much time did I have left?
About 4 minutes. You can
Oh,
take questions.
my gosh. I would have if anyone else had any questions. I can't believe it took nearly the whole time anyway. But no one really has any questions, right? This is kind of straightforward. No one's.
I think it's the sort of thing you kind of have to sit down and look at the diagrams and tables and puzzle over them for a while and blast
Yeah.
stuff into video memory for a bit. Kind of get the hang of it. It takes some doing.
Yeah. Thanks for your time, everyone. I appreciate that.
Thank you.